Let us continue our lecture of soil dynamics. In today's lecture, we are continuing with our module 5, that is machine foundations. A quick recap what we had studied in the previous lecture. We have solved a model example problem for design of block type machine foundation using Tschebotarioff's reduced natural frequency method. The problem statement was given to us with the size of the base plate, then weight of the machine, operating frequency of the machine, and it was asked for 3 different types of soil, how we can design the machine foundation. So, with this knowledge of K, which is required of course to calculate the natural frequency, because natural frequency we need root over k by m. M of course, we can calculate from the size provided. We know the m, what is the mass of the footing, but k we need to compute, that is computed using this expression based on theory of elasticity. So, for first type of soil, that is for G equals to 50 TSF, K is calculated as 4 into 50 into R naught is 1.521 by 1 minus mu is 0.25, which is coming as around 405.6 in the unit of ton per feet. Okay. For second type of soil, that is with G as 100 TSF, K is computed as 4 into 100 into 1.521 by 1 minus 0.25. You can see these are linearly related, 811.2 ton per feet. And for the third type of soil with G as 200 TSF, K is coming out to be 1622.4 ton per feet. Okay. Now, in the next step, we have to calculate the natural frequency for both the cases. Let us start with under tuned case. For under tuned case, F n is how much? 3000 RPM. F n, we can write it like this, k by m into 60. Do you agree with me? Omega is root over k by m, omega 2 f is omega by 2 pi, and revolutions per minute, that to second. So, that is why 60. Clear? Therefore, m comes out to be k by 2 pi f n by 60 whole square, or m equals to k by pi f n by 30 whole square, which will give us weight W is k times G by pi f n by 30 whole square. Okay. With this equation, now k for each of the G value, for each of the soil parameter, we know k value and f n value is known. So, how much weight is required, we can calculate back. So, let us do that. For first type of soil, that is G equals to 50 TSF, W is coming out, K how much we calculated? 405.6, G is 32.4, pi into Fn is 3000 by 30 whole square. How much we are getting? It is coming 0.133 tons. So, weight of the foundation required is W minus Wm, which is giving us negative, means theoretically no foundation is required. So, but as I said, we can provide the minimum size. So, whatever minimum size is provided for this case of undertuned is good enough. Now, the same thing if we want to do for overtuned, let us see how it comes. So, for overtuned case, we have Fn as 1000 RPM, right, and the expression remains same, that W equals to kg by pi Fn by 30 whole square. So, for the first case of soil with G equals to 50 TSF, W we are calculating 405.6 into 32.4 by pi into 1000 by 30 whole square. It is coming 1.2 tons. Okay, let me clear this point. The G unit, what I have told at the beginning, that is kg per centimeter square. What is that kg? kgf, kg force unit. Then only it is equivalent to TSF, okay, in weight unit, not in mass unit. Do not think that that is the mass unit in the G. Tschebotarioff's method is sufficient, not fully. It says after providing the foundation size, in this case it is far away from the whatever we are providing. So, it is sometimes required to cross check whether really the no resonance criteria has been satisfied or not. So, hence to do that we have to recalculate back. So, another procedure is from the provided section you calculate back your Fn and check the ratio of F versus Fn. If it is far away from 1, we are on the safer side. That is the reason why we are doing this. So, what we found for G equals to 50 TSF in both the cases of undertuned and overtuned, theoretically no foundation is required to be provided, but for the practical implications we provided the minimum size. That is why the minimum height of the or minimum thickness of the footing as 150 millimeter is provided. Coming to the third case, I am not doing the second case, that is repetitive. For the third case, so that I can show the difference at least, let us see what it comes. For undertuned case with case 3 of soil, that is G equals to 200 TSF, we are getting W as How much is K value for 200 TSF? 1622.4, right? 4 divided by pi into this by 30 whole square. How much it is giving us? 0.533 tons. Again, theoretically nothing is required. Let us check the overtuned case. With G value of 200 TSF, W is 1622.4, 32.4 by pi into 1000 by 30 whole square, 4.8 tons. Okay. So, in this case weight of foundation required is W minus W m, 4.8 minus 0.5, 4.3 tons. Now, this much weight is required to maintain no resonance criteria, from which what we will get? Area provided, A is how much? We had provided area 7.2656 feet square, right. So, height we had assumed 15 centimeter. Now, we have to determine height, so that this weight is provided. How much height is required? Then 4.3 divided by 7.2656 into unit weight of concrete is 0.0708, so much of feet. It is coming how much? See, 8.36 feet is the height. Now, your dimension, horizontal dimension in the two directions x and y and the height are disproportionate, isn't it? So, as a good designer, what we should do? Remember what we said earlier, A is, this A is minimum A to be provided. It is not necessary that we have to keep the clearance of 15 centimeter only, we can keep more clearance. So, the base design will be from this, what it follows, that provide larger A and relatively small h, that is the design decision. So, that this weight of 4.3 tons whatever is required is maintained. And another practical implication, when we are providing the sizes of these foundations, we have to be careful that we generally provide in terms of workable dimensions. What are workable dimensions? In terms of generally in multiples of 25 mm, isn't it? That is why 50 mm, 100 mm, 150 mm, these are the standard sizes. And the thickness, if you provide, you can, now you have to do a little bit of iteration, which will give you a good design. You can try with say 200 mm thickness of the footing, then how much area is required. Let us say you keep all around same clearance. So, you will get the idea of area, and your width to breadth ratio based on your size of the base plate is known, you will get the dimensions and convert them to close possible multiples of that 25 mm. So, these are the design guidelines you can note down, which I am not writing. So, as a practicing design engineer, you have to follow this aspect. After getting the weight, get how much is height is required. You have not provided this height, so you have to increase that height. Hence, it is required to be provided a bigger area and a relatively smaller height instead of giving a very long height and small area. So, let us provide a bigger area with a reasonably smaller height, but not less than 150 mm always. That is the minimum thickness as required. So, this is the way we do the design of machine foundation size using Tschebotarioff's chart. As we had already discussed earlier, this is the easiest method, because just using that Tschebotarioff's chart you are getting all these values of area and cross checking it with no resonance criteria. But drawback is nowhere you can calculate the displacement. Okay? On the previous day, when I have shown the plot overtuned and undertuned, so which zone we know it is safer to go. Like if we remain always on the leftmost part very close to the 0 axis of the natural frequency axis, it will be safer in that side. And if we go on very higher side of the mass, in that case, when the operating speed or machine is getting started, there is a chance that it goes through sometimes the resonance criteria also, because your operating frequency, it is not that it instantly picks up, it will start from 0 to that value. So, these are different conditions you have to check, and which one will be the safer design guidelines. As a engineer, you have to decide. Yeah, I have given here for the sake of completeness both the method, but when you are using your intuition for design, you go for the safest mode. And also, as I said, if it is mentioned reciprocating or rotating type of machine, it is well understood whether overtuned or undertuned, which one you have to take. Then there is no need to check for both the cases. Only for intermediate operating frequencies only we do this kind of both calculations. So, as a designer, we are always getting the choices or options for which mode to go and continue. So, let us move to next model. Our next design procedure is using MSD model, Mass-Spring-Dashpot model. In MSD model, for different modes of vibration, the soil spring stiffness and the natural frequency, how they are calculated, how they are modeled, it is shown in this slide. The first figure, this figure A, is showing for vertical mode of vibration. So, this is the applied dynamic load. In the z direction, it is vibrating. So, the springs are considered having a spring stiffness of Kz, that is in the vertical mode of vibration, vertical spring constant, and natural frequency of this system can be computed as natural frequency for vertical mode of vibration, that is why omega n z, which is equals to root over this Kz by mass of the machine plus foundation system. Whereas, the second figure, it shows sliding mode of vibration, that is, it can be lateral in the direction of x or longitudinal in the direction of y, with spring constant k x in this direction and applied load is dynamic load in this direction. So, the natural frequency of the system can be calculated omega n x as root over k x by m. Coming to other two modes, rocking mode of vibration, this picture shows rocking mode of vibration. Applied dynamic load is acting like this, it is rotating about this point O, and angular or rotational displacement is phi. So, in this case the natural frequency of the system is computed omega n phi as root over k phi. K phi is nothing but rotational spring constant in this rocking mode, divided by m naught is nothing but mass moment of inertia about this point O, about this rotational point. So, similarly for pitching also the similar expression will hold good, only it is about y axis, the other one will be about x axis, but basically the expressions and nature of equations everything remains same. Whereas, for yawing mode of vibration, yawing means when it is rotating about the z axis, applied load is in this direction, the natural frequency of the system is calculated like this, omega n phi, sorry omega n psi, this was phi, omega n psi is equals to root over k psi by m z. M z is nothing but mass moment of inertia of the system calculated about this z axis. So, this is mass moment of inertia calculated about z axis. K psi is torsional stiffness of the system. Okay. Now, let us define some terminologies. Coefficient of elastic uniform compression. This is generally denoted by Cu. So, what is Cu? Mathematically, if we express, it is nothing but uniform compression by elastic settlement. So, say small p by S e, which actually we had seen for cyclic plate load test. Can you recap? This is uniform compression is nothing but load per unit area by elastic settlement. So, using this, what we can compute? Kz, that is spring constant for vertical mode of vibration, that is given by P A times S E. Therefore, Kz is Cu times A. That is the use of this coefficient of elastic uniform compression, from which you can compute vertical spring constant for vertical mode of vibration, and A is the area of the base plate. Another terminology, coefficient of elastic uniform shear, C tau. Here the relationship is k x equals to C tau times A. So, using coefficient of elastic uniform shear C tau, we can get the horizontal spring constant k x or k y in whatever direction we are considering the shear, multiplying with the area A. Next, another terminology, coefficient of elastic non-uniform compression, that is C phi, denoted generally by C phi. K of phi is related to this as, so K of phi calculated using coefficient of elastic non-uniform compression times the area projected, whereas coefficient of elastic non-uniform shear is denoted by C psi and K psi is calculated as C psi times A. So, these are the 4 terminologies or 4 parameters which can be obtained from test, and then they can be used to compute your spring constant for respective mode of vibrations, whether vertical, whether horizontal, whether rocking or pitching, or whether yawing. How it is done? Generally, what is the standard procedure for from the test, field test? We compute the first one, that is Cu, or sometimes it is called Cz also. Let me put it back here. Either Cu or Cz. Earlier we had used Cz. You remember, for your lecture on cyclic plate load test, we had used Cz also. That is also used. So, we compute Cz, and other remaining parameters we generally compute from the relationship between these individual coefficients. It is easy to determine the relationship between coefficient of elastic uniform compression and coefficient of elastic uniform shear and other coefficients. So, you can note down these coefficients are correlated. Now, Barkan in 1962, it proposes some correlations of Cu with other parameters. Cu is about 2 times of C tau, C phi is about 2 times of Cu, and C tau is about 1.5 times of C psi. So, these are the 3 expressions which can be easily derived just by using the compatibility of different modes, equating their spring constant and their relationship for different modes of vibrations, from which you will get in the site, as I have mentioned, we just determine Cu, and then using these expressions we calculate C tau by using this expression. Once the C tau is known, C psi also can be obtained, and from Cu we can get C phi also. This is the way we calculate generally all these coefficients, and then from these coefficients we will get the spring constant in our analysis using MSD model, because in MSD model we must know the spring constant, then only we can proceed further. What our IS code says, IS 5249, it recommends the value or relationship of Cu as 1.73 times C tau and C phi as 2 times Cu equals to 3.46 times C tau. So, these are the relationships given by IS. These are nothing but factored relations which can be used for the design purpose. So, now using MSD model for each of the modes of vibrations, let us see how the design can be done. Let us look at here. First, we have to do the analysis. In vertical mode of vibration, this is the block type of foundation, block resting at a depth of df below the ground. This is the embedment depth. Base area is A. This is the dynamic load P naught sin omega t. And in the second picture, it is showing block resting on the surface of the ground, which is always obviously not the case. We have to provide a minimum embedment depth always of 150 mm. Soil, if it is replaced, this soil is replaced by the equivalent spring, then Kz are the spring stiffness in the vertical mode of vibration. And if we put it in our conventional single degree of freedom mass spring system, it will look like this. Obviously, if we add the dashpot also will come into picture. So, what is the equation of motion for single degree of freedom? Ignoring dashpot, it will be m z double dot, that is z double dot is nothing but acceleration in z direction, and k z times z is p naught sin omega t. And k z we have seen equals to C u times A. C u is nothing but coefficient of elastic uniform compression, we have already mentioned. So, omega n z, that is natural frequency, is calculated root over k z by m, which is nothing but k u A by m. Now, C u is already obtained from the field test, as I have mentioned. So, you can get your k z, from which you will get your omega n z. How the amplitude of motion is calculated? Amplitude of motion A z. Why A z? Because in the vertical direction this amplitude will come, right. So, this will be p naught sin omega t by k minus m omega square. This we had already derived in our MSD model analysis. So, if you put the expressions here, it will be m times omega n z square minus omega square, where this omega is exciting frequency and omega n z is natural frequency of the system in z direction. And this maximum amplitude will be obviously not this sin of omega t will be involved. So, p naught by m times omega n z square minus omega square, this value should be less than 0.2 mm as per our IS design codal guideline. And also this A z value has to be checked with Richard's chart for the third criteria, that is, it is not annoying to the people working in the surrounding vicinity or to the adjacent structure. So, these two has to be checked. Now, if the damper is involved, which is the practical case, obviously, this equation will involve the damping ratio also. You know that equation, right? The expression will be A z, that p naught by k root over omega 1 minus r square whole square plus 2 eta r whole square. So, that is the expression. So, remember it is nothing but the same whatever we have studied in our module 2, that is to compute the amplitude in the vertical direction. Okay? There is nothing new as such, only the design procedure has to be followed, and where from you will get the k value, these are the guidelines. Coming to next mode of vibration, that is sliding mode of vibration. Now, in the case of sliding mode of vibration, this is the applied dynamic load and sliding displacement is x. So, our equation of motion is for a single degree of freedom system m x double dot plus k x x equals to p x sin omega t. K x is that horizontal stiffness, which can be calculated as C tau A. We have seen just now C tau is nothing but coefficient of elastic uniform shear. So, natural frequency of the system omega n x is nothing but root over k x by m equals to root over C tau A by m. And here how we compute the maximum amplitude of motion A x? Amplitude of motion equation will be exactly same for vertical mode also, only difference will be this suffix will be in terms of the sliding direction, that is in x direction if we are considering x, k x and p x, and maximum value will be A x is p x by m omega n x square minus omega square, that also needs to be less than 0.2 mm, and it again needs to be checked with Richard's chart. Originally it is Blake's chart given in Richard's book, right. So, for horizontal mode of vibration, that needs to be checked. The same expression. So, if damper is involved, it will be p x by k x root over 1 minus r square whole square plus 2 eta r whole square. Okay. There is no difference, only instead of vertical here it is horizontal. Now, let us come to rocking mode of vibration. Rocking mode about this point O, it is rocking, this is our x axis. So, the axis perpendicular to this plane, that is coming out from this is nothing but our y axis. So, m y applied dynamic load m y is nothing but, let us say it is harmonic. So, m naught sin omega t, m naught is the amplitude. So, that is why it is creating this rocking mode of vibration for the foundation. And when it is subjected to this kind of rocking mode of vibration due to the load m y, the weight gets shifted from this C g to this C g. Okay. And let us say L is the height at which the C g of machine plus foundation system was existing. L is the height at which from the base of your footing, the C g of entire this foundation plus machine system is located. So, that will be shifted here. Let us say for small angular rotation, phi is our angular rotation, this distance will be L phi. How the pressure will get generated at the base of the footing because of this type of rotation? Pressures will be, pressure distribution will be this rectangular uniform pressure is nothing but static pressure, right, P S T, and the dynamic pressure will be here compressional, here tensional. So, that is why the hatched portion is nothing but our dynamic pressure getting developed at the base of the footing. Now, let us consider that A is the dimension of the footing in x direction, L is this length at which we are considering an small infinitesimal strip, where the dr is nothing but the soil resistance or soil pressure, and dA is the area on which it is acting. So, moment due to this soil reaction, at this infinitesimal place, it will be dr times dA times this L, moment about this point O, about this axis, is not it? That has to be integrated over the entire area. So, if we express it in terms of the soil properties, the reaction, it will give us C phi L phi dA times L, C phi phi over the entire area dA L square. It will finally give the expression C phi times I times phi, and it acts in the anticlockwise direction, where this dr is soil reaction acting over the small area dA, L is the distance of dA from the center of rotation, phi is angular displacement of the block, and I is moment of inertia of the contact area about an axis passing through the centroid of the base contact area. So, centroid of rotation in this case perpendicular to the plane of the vibration. So, remember in this case I is area moment of inertia, not mass moment of inertia. Okay. So, C phi I times phi, this will give us the moment due to the soil reaction. Now, in this case it is assumed that the soil reaction dr at any point is proportional to the displacement of L phi, and at that point C phi is the constant of proportionality. That constant of proportionality is nothing but what we have defined as coefficient of non-elastic, non-uniform compression, right. And moment due to displaced position of the CG, because of this rocking mode of vibration, this CG has shifted from here to here. So, because of that the moment generated is nothing but W into L phi. For small rotation we assuming this, we are neglecting this component, we are considering L phi, right. So, W times L phi is giving the moment due to displaced position of the CG, and what is externally applied moment, that is dynamic load, nothing but m y is m naught sin omega t. Now, to maintain the equilibrium, or in other words if we say, if we apply the D'Alembert's principle, it should give us that whatever inertia force is coming for the foundation system, which is nothing but the rotational acceleration is phi double dot and mass moment of inertia is m naught. So, m naught you can note down, it is mass moment of inertia about this axis, about this point O, whereas I is the area moment of inertia. So, do not get confused, this is area moment of inertia, whereas m naught is mass moment of inertia, because here the inertia force is involved. So, this mass moment of inertia times acceleration will give us the inertia force, which should be equated with sum of all other moments which are getting generated externally. Externally because of the reason of soil pressure, displaced location of CG and the applied moment. Clear? So, what is coming? M naught sin omega t applied moment, C phi I phi, we got it from the soil reaction, W L phi we got it from displaced CG location. Sum of them should equate with the inertia force getting generated in the system, which you simplify, you will get in the our conventional or canonical form of equation of motion, that is m naught phi double dot plus phi times C phi minus W L. So, it will be nothing but our resultant k phi. Am I right? This is nothing but resultant k phi equals to m naught sin omega t, the equation for a single degree of freedom system. Now, this natural frequency omega n phi, that is calculated as root over k phi by m naught. Now, k phi is nothing but this one. So, in practice this C phi is much more than W L. So, we can consider this equals to root over C phi I by m naught, and maximum displacement A phi will be this m naught, that is externally applied moment amplitude divided by naught, that is mass moment of inertia of the system about axis O, times omega n phi square minus omega square, so much of radian. In this case, I will be what I was telling you, the area moment of inertia, that is nothing but for a rectangular foundation b a cube by 12, where a is the dimension in the direction of about which it is rotating, right, and b is the another horizontal direction in the perpendicular direction of the foundation. Clear? So, a is the dimension in x direction and b is the dimension in y direction, and f n phi obviously can be represented by this expression. Now, if I ask you how we will check this maximum displacement a phi in terms of the guideline or stipulated displacement or the reference displacement, can we do that? Yes, this is angular displacement. If you multiply this with respect to your height, you will get how much is the projected linear displacement, right. That will have to check against that 0.2 mm. Is this clear? So, if we multiply this with the height, you will get the linear dimension of the maximum possible displacement, that needs to be checked with 0.2 mm, which is specified value. So, with this we will stop our lecture today here. We will continue further in the next class.